All right. Today we're going to be looking at sections 1, 1, 1, 2. We're going to look at patterns. Patterns in mathematics. What's the point of them? What's the big deal? Here we go. Mathematics is a tool that we use to describe the world around us. That's what we're doing. Okay? That's what math is all about. It's not sitting down doing a bunch of little stuff on a piece of paper. It's looking out in the real world and saying, why does that work? How does that work? Can I express that in a numerical and an equation or something like that? To do that, we need to look for in the real world, we look for patterns. Most of mathematics is people observing stuff in nature and recognizing, can I represent that in a pattern? Is it happening the same way each and every time? So we're going to be looking at how do I find these patterns, and then how do I use them to make predictions about the thing coming up, or make an inference of stuff. That's what we're going to be doing, and I'll talk about those a little bit more. Everything we do in this class is going to help us develop that skill. That's what we're doing in this unit 1. It's learning how to recognize patterns, okay? How to recognize what kind of pattern we have, how to describe those patterns to other people, okay? And then to use those patterns to make predictions or inferences. That's what we're going to be doing in this unit, okay? So as we go through each of these lessons, it's vital that you document any concept, skill, technique, or procedures that you know or learned that you can help you with future work. Okay? These are the foundations of your study notes. These are just basic techniques. These are not set in stone. These do not work all the time. These are things you need to think about as you go through your work. So depending on what you're looking at, if I give you patterns in pictures, like in number 1 over here, the first one here is a picture pattern. Pictures. If I have pictures, you want to change them to numbers if it is possible to do so. You want to organize your data, your observation if you're out in the real world. What am I observing out in the real world? Okay, that's your data. Put that into a table. Okay, so put the data in numerical order. These are things that you can do also. We're trying to find patterns. So when I find a pattern, here's some questions that I can ask myself. Can I find the next number if there is a relationship between the previous data? Okay. Can I continue the pattern? To continue the pattern, this kind of a situation is actually defined as a recursive rule. Can I use previous information to predict the next number? So can I get the next number from the previous number? That is a recursive technique. If I put the data into a table and I number it in order, so this is the first number I got, this is the second number. So if I give it an order, a position, can I find a pattern between the data and the position the data is in a sequence? Can I find the answer, the third number in the pattern, by knowing that it's the third number in the pattern is what I'm getting at? Can I find the 27th number in this pattern, knowing that it's the 27th number in the pattern? Just by knowing its position, can I determine that? And that's called an explicit rule process. We'll talk more about this in much more detail as we move along. Once we organize our data, we want to try and find this pattern algebraically, but we can also draw a picture of the data. By drawing the picture of the data, we can see we might be able to see its relationship to the data and places around it. So that's what a graph is for. A lot of times in the past, you may have been asked to graph something. And you go, okay, I'm just doing this. But you got to understand that graph that you're drawing is a picture of the information. So it's a visual that the equation is saying. So you have the equation or a pattern that you described, your algebraic, and then the picture of it. It's two representations of the same information. Okay? We can use the visual to help us determine what kind of pattern is there. We're going to talk about that also. When we draw graphs, okay, the input data, and we'll talk about that here in just a minute. We usually do a 2-axis graph. We'll have a horizontal graph and a vertical graph. And the input data goes on the horizontal, The output data will go on the vertical. Each axis is a real number line, and they cross each other at 0. Again, I'll describe this and draw you pictures of all this here in just a little while. Well, I'll just do it now. So here would be input data would be in a horizontal number line. You've had these all growing up in math. You've seen these all kinds of things before. This would be your horizontal data, positive numbers on this side, negative numbers on this side. This would be where the input data goes. And if we draw a line this way, another number line, this is where 0 is, then the marks go up this way. This is 1, 2, and 3, and the negative numbers go down below. So this would be the input. We actually have a different name for that. And this would be the output. Also has another name. So we can graph and put data in this format. I can do these little marks can be numbered differently depending on how much data and the size of the numbers that we have involved. Just know that they don't have to always be going by ones, and they don't always have to be numbered the same way. This one can go by ones. This one can go by 5s, depending on how big the numbers are. These are just all things that are out there. I don't expect you to memorize everything at this moment. So I'm just giving you some information. When we put data in here, we should put it into a dot. So it has some representation, and we'll put a dot in there. That's usually what we do. Okay? Then we put a bunch of dots, and then we can see a picture. The more dots I have, the more clear the picture is, just like on a TV screen. Okay? TVs are made out of a bunch of little tiny dots, if you did not know that. The more dots you have, the clearer the picture is. Once we have a bunch of dots, we don't connect the dots automatically. It depends on the story, the situation, okay, in context. Sometimes we will connect the dots, sometimes we will not. A discrete type of data is the kind of information that you do not connect the dots. Okay, you don't connect the dots in discrete. It's used to describe how many objects you have. Objects cannot be split apart. In other words, if I'm trying to put a bunch of dots on here representing the number of people, there is no dot halfway between 1 and 2. You cannot have half of a person represented. It's only whole people. So therefore, that would represent what's called a discrete graph. You do not connect the dots. Whereas in continuous, this is the ones where we do connect the dots. And this would be stuff like time. I can have the little marks here represent seconds. But is there a half a second in time? We don't go through life just jumping from second to second. There is a smooth, continuous movement in time. So there are fractionals of seconds and even really small parts of seconds and things like that. So a second graph would be one that would be an example of continuous data. You're also going to do some, when we do a situational graph, so graphs based off of real life scenario, these axes get named. Here I put input and output, but if this input represented number of people, then I would just put number of people. So you would have to title it according to what it represents. That's what we're saying right here. All right, so there's a lot of stuff right there. I got more, and this is more in line with the pattern stuff that's going on. There are 2 types of patterns we're going to, or not 2 types, there's 3 types of patterns that we might look at coming up. And I'm going to explain these in a little bit more detail. Here's some things we can do. You know, I'm going to just do it here with an example. I'm giving you a bunch of numbers here, and this pattern keeps on going. So this right here is a sequence. It is a sequence of numbers. Okay, just a collection of data. A sequence of numbers, and each individual one is a term in the sequence. Okay. If I see a pattern like this, what we want to do is we want to be able to look at it and say, can I predict what the next number is based off of what I see now. Okay? Remember, that's called the recursive technique. So if I asked you what the next one was, well, we got to look at this and see, well, can I see a pattern here? Well, sometimes the pattern's easy to see. Maybe in this case it is for you. Sometimes it's not so easy. So some of the things that you can do is, number one, like we said, we can put this into a table. If I put it into a table, then I'm placing in here positions. So usually what we do is like, what number in the sequence are you? Well, and then down here, they use a lot of different things, but we'll call it this. They usually use an A with a little subscript that represents that number. So the first number here in the sequence would be the number 3. And they would designate in the symbol format, this right here is called A sub 1. The first number in the sequence called A is really what it boils down to. What's the second number in the sequence? 1. So this would be A sub 2. Okay, they're not exponents, they're just a positioner. A sub 1, A sub 2. It means the second number in the sequence. That's what it refers to. What's the third number? -1. The fourth number, -3. The fifth number, -5. The sixth number, -7. And it continues on. Okay, so generically we can say all the way out to some number k. So what is A sub k? What is this going to be? And usually what it is it's your rule. It's a rule that you found for this pattern, an algebraic rule. But we're ahead of ourselves at that point. So what I want you to look at is, I'm trying to get a feel for this. I can graph this data. See, now if I look at it, this would be my input. This would be my output. The input, the output. So another technique is this. This is called the first difference. Subtract these two numbers. When you subtract them, it would be the right one minus the left one. The right minus the left. It's always right minus left. Right minus left. So 1 minus 3. 1 minus 3, -2. So 1 minus 3, -2. Subtract those two numbers. Again, right minus left. -1 minus 1. -1 minus 1, -2. Subtract those. -3 minus a -1. A -3 minus a -1, -2. Hopefully we're starting to see a pattern here, aren't we? Each one of these has a difference of -2. If you see this pattern emerging on the first differences, your pattern is linear. And I'll talk about that in a minute. And what that means. The pattern becomes linear. And usually what that means is we have a rule format that usually goes like this. Let's put it this way. I don't want to get it too carried away. Your output is basically a number times your input plus another number. This is a number, and this is a number. So that means you're going to take your input, you're going to times it by a number, then you're going to add another number. This is linear in nature. So this is the idea right now. There are other patterns that are going to come on, but I'm going to hold off on it now. Okay? And then we'll come back and look at them. No, actually, I take it back. Here's another type. This is a linear one. Here's another one. I'm going to put it right into a table. This is my input. This is my output. And I can start at 1, 2, 3, 4. This would be 3. This would be 9, 27, 81. When you do this, you'll notice that if I do the differences, 9 minus 3, I'll get 6. That minus 9 is not 6. So it's not going to do the same thing this one did. Okay, so this is not going to be linear. But I noticed something interesting. This is 3. This is like a timesing by 3. So look at it this way. If I can take 9 divided by 3, I get 3. If I take 27 divided by 9, I get 3. If I take 81 divided by 27, see, I'm dividing the two consecutive terms, right? I get 3 again. This kind of a pattern describes what's called exponential. That's an exponential in nature. And in this case, your output is, I'll just keep it simple, this one. This right here is called your common ratio, is this number 3. So it is your common ratio, okay? And then up here will be an exponent. Something to do with your input. There's more to that, but that's your basic format. I'm going to leave it with those two, and I'm going to go over here to the classwork, and we'll do a couple of examples and show you what I'm kind of looking for. And then we'll end this video. The rest of the video, the notes are these right here. I'm going to leave it here, so if you look at it later on, you can come and pause it, zoom in and pause it, and kind of write these things out. This right here is going to represent the other example that is a quadratic in nature. Like the linear, it has a second difference. That's how you can tell. And it follows this kind of a pattern. It's hard to read because I haven't zoomed in, but so a second difference means you know you're going to have a quadratic equation in nature. And again, we'll explore this in much more detail as we practice a lot. So there's the notes right there. I'm going to walk you through an example off the classwork. We'll pick one of these over here. I want to talk about the fraction, so you can see how to deal with the fraction. The first thing you should do is take your sequence and put it into a table. We'll use n, and we'll use a sub n. The first number in my sequence is 10. The second number in my sequence is 5. The next one is 5 over 2. The next one is 5, excuse me, this is a 4. 5 over 4. And the next one is 5 over 8. So the first thing I'm doing is I'm looking at, in general, what do I see? In a fraction setting, so basically the reason I chose this one, for fractions, the numerator, the top, and the denominator have separate patterns, so you do them separately. Separate patterns. So usually that's what I do. The numerator has its own pattern. The denominator has its own pattern. Okay? We can also look at it and see what's going on. What's happening from 10 to 5? It's cutting in, if you look at it, it cut it in half, didn't it? Cut it in half. What's going from here to here? Well, 5 over 2 as a decimal is 2.5. So hopefully that helps you see that that is just basically we're cutting it in half. So in each and every time, if I can see this pattern, it looks like I'm just dividing by 2. Divide by 2. Divide by 2. Each and every time, that's what's happening. Now, it's hard to see that one because I just got done saying that this here represents a, but dividing is the same as multiplying. So this one is going to look at an exponential pattern, but we'll beyond what we're doing. So the tops we can see are all the same. It's going to be a 5 for the rest of these things down here, but the bottom number is going to be going up by 2, timesing by 2. What would you say is the next number in this pattern? Well, if each one divides by 2, if I take a number and I divide it by 2, I want you all to recognize that that means exactly the same thing as a divided by 2 or a times 1/2. All these three things mean exactly the same thing. If I look at it as timesing by 1/2, it's a little bit easier to see what to do next. Instead of dividing by 2, think of it as timesing by 1/2. So then you have a 5/8 times a 1/2, and I get the next number in the sequence, which is 5 over 16. So that's how I can get this. This is kind of what we're doing today. We're looking for these patterns and describing them. What description would I have here? I would say I'm going to either divide by 2 is one possible description to get the next number. I can multiply by 1/2 to get the next number. Both of those are excellent descriptions of what was going on. So I'm going to stop the video right there, and we're going to talk about a bunch of these things.